Hi, I'm Justin.
And I'm Michael.
And this is our podcast where we discuss what we find interesting about the intersection of Web3 and digital security as we know it.
Between us, we have years of experience securing digital products and infrastructure, which has led us to be constantly curious about what's next.
Which is what this podcast is about, sharing our journey as we update our mental models for security in the next internet.
Hello, and welcome back to Not Your Crypto Podcast with myself, Justin, and my amazing co-host, Michael.
Thank you. How are you doing, Justin? I'll ask you this time.
I'm okay, a little bit tired, did a bit too much this week, but otherwise, I'm here. I'm here in the flesh and in the spirit and mentally, hopefully.
Good.
How are you doing?
I'm doing good. Actually, here's a fact. I was trying to think of facts that I didn't tell you before we hit start recording that I could use right now. Here's one. Did you know that Windows now ships with like an entire Linux subsystem on it, like environment on it?
Oh, wow.
Like one command and you're running like Ubuntu basically in PowerShell. Yeah.
That is super cool.
I just learned that. I think that's old news, but like...
No, I did not know. I mean, I haven't been on a Windows box in...
Yeah, I know, right?
A really long time.
And it works pretty well, at least so far for me.
Yeah.
Like I'm doing dev on it and stuff, and it works pretty well.
I'm trying to think what that application was that I gave you a Linux prompt in Windows command line.
Like back in the day?
Yeah.
Yeah. I forget what it was called.
Yeah, you know the one I'm talking about though, right?
Yeah.
Oh, man. Okay, well, okay.
But this isn't just a prompt. This is a full environment,
this
file
is a
system.
full environment. Wow,
yeah.
That is super
You can
cool.
install dependency like apt-get, whatever.
Did you discover it by accident or did you just...
I was Googling around how to do development on Windows machines because I was like, what? Can you do that? And most people just use it like, well, it depends on what you're developing or whatever. But yeah, most people just use that to run a Linux environment inside of it and then do development in there. Anyway.
That is super cool. All right, on to today's topic.
Yeah.
For those who have been following us and are keen-eyed, you'll know that today it's time for a technical analysis. These are very straightforward episodes, to be honest, where we take an interesting, obviously, security bug. Most of the time, it's obvious because both of us are security engineers. And we kind of we look at it technically, but we don't delve too deep into the weeds, or we don't dwell on the details for too long, but we like to talk about what happened, why it happened, and where we think where we try and draw parallels to Web 2 instances of the same thing, or where there are lessons that could have been learned from Web 2, or where this doesn't have a parallel on Web 2, it's a strictly Web 3 thing, and what Web 2 could learn from it. In this case, we have the Binance hack from October 2022. Keep me honest here, Michael. I think
that's correct. Yeah, about 2 years ago, right?
Yes, it's about 2 years ago. This was an interesting one. I do remember the headline flaring up at the time. I do think you and I discussed it briefly and then moved on with our lives. And now we've taken a deeper dive into it. It's still a very interesting hack that took place. The headlines, it was a hack from October 2022. 600 million USD was taken. It was huge. That is obviously quite a chunk of change. Like, that is a serious thing. And the thing is, it wasn't Binance's only hack. So I'll leave that as an exercise to the listener to go and Google the other hacks of Binance. Binance, by the way, is a centralized exchange. A centralized exchange in the Web3 world is basically a place where Coinbase. It's an equivalent of Coinbase. You go, you want to buy a token, they sell it there. And then they do a bunch of other decentralized financial things as well, which we won't go into because they're detailed and we don't really care about most of those things in this podcast, and it's not it's not relevant to what we're going to talk about today. But yeah, so Binance is a centralized exchange and they got taken for $600 million. Those are the two headlines. So Michael, what did you think of this? Tell us what interested you about this topic, etc., etc.
Yeah, cool. So should I start describing it, or where should I go?
Go with
what's interesting about it.
What is interesting about it? Why it happened in the first place? Like, what was the thing that was exploited?
Yeah. Okay. Cool. Yeah. Okay. So Binance runs a centralized exchange, right? But the issue that we're talking about here doesn't so much. This wasn't like an exchange hack, right? This wasn't like the. I think I've only ever read this. Mount Gox. Is that how you say it? Okay, I didn't want to be the first one to say it.
That's what I've only ever read it already. I don't know.
Yeah. This isn't like somebody hacked into their servers, got access to a key, and absconded with X million dollars or whatever. This was a Web3 or a crypto sort of native issue.
Yeah.
in some chains that they were running.
Yes.
So at the time, Binance operated at least 2 different blockchains themselves, right?
Yeah.
So this is like, we're not talking about Ethereum, we're not talking about Bitcoin, we're talking about blockchains that Binance ran. There was one that was a governance sort of chain for some stuff, which I think was the older one.
Yeah.
And then there was a newer one that was, they called it like Binance Smart Chain, I think, right? BSC.
Yeah.
Which was a layer 1 chain. So like, the like equivalent of like the Ethereum mainnet sort of chain, like the lowest low level chain that was EVM compatible. So you could run smart contracts on it. And it was used for, running Web3 applications on top of and all that. Right. So the reason why like this got interesting to me is because the vulnerability was in the bridge between these 2 chains.
Okay.
So bridges are one of those things that are way back when we first started talking about crypto and Web3.
Yeah.
Bridges were one of the first topics that we talked about, I think.
Yes, they were, because they're a strange existence. They don't have
They
a
are
parallel.
strange things.
Yeah,
they feel very strange, right?
Yes.
Like if you were to here's one way to think about it. If you were to describe how blockchains work to me, I'd be like, okay, cool, right? Like, that doesn't tell you anything, but I'd be like, okay, cool, that's how blockchain work. I get it.
Yeah.
And then you were to tell me, oh, and you can also transfer assets from one blockchain to another in a way that's completely native to the blockchain.
Yeah.
That kind of breaks my mental model of how I think a blockchain works, right?
Yeah.
To me, like a blockchain is like a self-contained ecosystem. Like, what do you call that in physics when like something only ever has forces within itself and forces from outside don't come in? You know what I mean?
I know what you're talking. It's gone.
There's a word for that.
Exactly. There is a word for it. Yeah.
Yeah. Anyway, to me, they're like these self-contained things, right? But when you talk about a bridge, you're actually like interacting with something. You're interacting from within that blockchain with something that's outside of that blockchain.
Yeah.
And just something about that to me like doesn't feel like it should work, but it actually
does the same thing for me. And the reason it does it for me is from a low level technical perspective. Each blockchain L1 tends to have its own technical cryptographic rules. So I'm like, okay, I don't understand how you're going to import one or export to the other when they are completely, it's almost like you said, if it, like, to bring up your physics analogy, there are different universes with different fundamental forces.
Exactly,
as far
right?
as I'm understanding.
Yeah.
So one cannot, an asset from one should not be able to exist in the other. But lo and behold, it's technology, and we made it happen.
Yeah, it would be like if you said, like, actually, we live in a multiverse, and the other universes can like transfer stuff into our universe. You'd be like, wait a minute, I don't know about that. But anyway,
sure that works.
But what is like at a high level? So at a high level, a bridge is a function that lets you transfer assets from one blockchain to another.
Yeah.
And usually back the other way as well. Like
Yes.
Transfer assets from one blockchain to another.
Yeah.
Assets being tokens.
Yeah.
By and large, right?
And so that's where the need came in, I'm assuming, is I have a bunch of Ethereum and I want to trade that for Binance's token. I want to buy Binance's token with Ethereum. I'm assuming this is where the need came from in DeFi.
Yeah.
And so...
Yeah. Exactly. Like, you know, at first there were few blockchains. Then there was a phase where like everybody was making blockchains for all sorts of different reasons. It became fractured. But you wanted to do things across them, right? And exchange them in a decentralized way or whatever.
Yeah.
So in this case, there was a bridge between Binance's two chains that they ran. So between that kind of beacon chain, they called it, I think, the governance chain, and the BSC smart chain, so that you could transfer assets from like the governance chain to the smart chain. Transfer tokens. Yeah. So, but like, is it useful to say like what is practically what a bridge looks like? Should we talk about that?
Yeah, I think, because one thing I do like to do on this podcast is get away from the nomenclature just to break it down. So everyone understands that, well, people who know blockchains understand that any application is supported by smart contracts. That's exactly what they are, decentralized bits of code that are hosted on the chain and run. A bridge fundamentally is a smart contract. That's a fair characterization.
This bridge is, yeah. There's different ways to do bridges.
Oh, okay.
There's different like kind of classes, categories of bridges that you can have.
Okay.
So like, and this kind of bridge actually is the one that makes less sense to me. Harder for me to understand.
Okay.
Like, so what one category of bridges is, I think they're called like validator-based bridges. I don't know if I have the right term there, but basically the idea is a bunch of actors in the ecosystem like kind of put liquidity into like a wallet on the blockchain.
Mm-hmm.
And then when you want to transfer assets, they kind of like lock up your assets on one of the chains and then release assets to you on the other chain.
Yes.
And then that can be reversed. So you're kind of like sending your assets to this place that locks them. And then these validators or whatever that are like providing kind of liquidity to the bridge, then unlock assets for you on the other chain.
Yep.
And there's usually some kind of like governance mechanism or consensus mechanism or whatever between these validators to kind of ensure like the different kind of honesty or security kind of guarantees that you want there. I don't know. That might be like a completely incorrect characterization, but that's my understanding of. That's the one that kind of makes more sense to me.
Yeah.
This kind of bridge is sometimes called I think it's sometimes called a light client bridge.
Okay. Yeah.
And it is fully a smart contract. It is like, I don't know if 100% is too strong, but it's like fully implemented as a smart contract. So in this case, on the BSC chain, like on the smart chain, there was a smart, I'm using past tense because like the hack was in the past. Some of these things may still be true. I'm not sure. Didn't do that much research. There was a smart contract.
Yeah.
On the BSC chain, and that smart contract was built to track this kind of like the state of the other chain.
Yes.
And we can get into the details here a little bit more, maybe in a second, but like it had like a data structure basically that tracked the state of the other chain.
Yeah.
And so when I sent on the other chain, like on the governance chain, the sending chain, I guess, when I sent my tokens to like an address in order to have them transferred, I would then take what you would call like a proof. Like I take like a cryptographic proof, which is also kind of a data structure. That I made that transaction on the other chain.
That it finalized.
That it finalized. Yeah. I take that proof to the receiving chain or like the target chain to this smart contract and say, hey, on this other chain, I sent this transaction because I'm using your bridge. Here's the proof that I sent this transaction. And then the smart contract on the receiving chain is able to verify that proof. It basically like the code of the smart contract is able to knows how to verify that proof. And then says, okay, I do see that you did actually do this. And then releases or mints tokens to you on the other chain.
Which is dependent on whatever the details of the transaction from the origin chain were. So basically, if you say, I want 20 BNB and I'm sending you 30 F, that transaction that is finalized on that original chain, that's what it then mints on the target chain. It then says, oh, okay, you've done this transaction, has been finalized, consensus has been reached on that original chain. I can validate all of that with this cryptographic proof you've given me.
So,
and here's your 20 BNB.
Exactly. So Justin, security mind that you are, what's the important bit here? What's the important bit to how the bridge works?
The important bit to how the bridge works is it all comes down to that cryptographic proof. Everything hangs on that validation process.
Yeah, which is what crypto likes to do, right? Like the blockchain world, the crypto world, the Web3 world likes to like root the security guarantees in cryptography, obviously, right? Like in cryptographic proofs. We like to reduce things to like relying on the blockchain to implement the security guarantees and all that. Like, it's a difficult thing for me to understand, like how this works. But the idea and the impetus for kind of building these kinds of bridges is that we don't want a third party that's providing liquidity, providing validator kind of stuff, whatever. As much as possible, we want to be building on these crypto primitives, these like native concepts in this world to provide this functionality.
Yeah, because obviously, who's ever implemented cryptography and made a mistake?
No one.
That's never happened. Look, and again, I always premise these episodes with, we're not doing this to laugh at people or denigrate people's work. We're doing this literally to learn from the mistakes that people have made. But we understand why these things happen, and mistakes will continue to be happening. We're not trying to be on our high horses looking down on saying this should never have happened.
Oh yeah,
but
totally,
mistakes
totally.
happen, and crypto is hard. Implementing crypto is hard, and this is another example of where mistakes can happen if you don't do thorough testing. And even if you do thorough testing, you can still have these things crop up.
Yeah, absolutely. And I think like it's, the way these things break are going to teach us about the new world, right? Like the way that stuff breaks here is teaching, gives us a feel for what Web3 is like, what the kind of blockchain world is like, right?
So then, to further talk about the technical details of what happened here. So going back in your example, whereby you want to initiate this token swap, this asset swap, so to speak, between these two different chains, the original chain, the target chain. I think it was BSC. Anyway, the smart contract.
There's a lot of acronyms thrown around.
Yes, there is, and I'm trying to stay away from them as well, otherwise people can fall asleep. Basically, from the original chain and target chain, who is it that is able to submit, when you say you as a user, they submit the transaction to the chain, but they don't submit the proof themselves, do they? Something does that on their behalf. There's another component involved here, correct? That component is a relayer,
That's right. Yeah. So I think there's different ways to construct the ecosystem here. Like, I think in some cases, so basically I'm the user. I want to use the bridge. I send a transaction to this place to use the bridge. Something needs to kind of courier that from one chain to the other chain.
Yeah.
And then call the smart contract saying, this action happened on the other chain. Like this entity, this user is trying to use the bridge. And kind of relay spoiler alert, relay that message from the chain 1 to chain 2, right?
Yeah.
So those entities are called relayers. You can go. But
go on.
And I think there's different ways to construct that player. Like, I think in some cases, I think that's like completely open. Like I think anybody can be a relayer in some implementations of this, because the idea is you're not relying on the relayer for the security of the bridge in kind of the idealized state here, because what's important, like the cryptographic proof is the proof.
Yeah.
And it's, again, in kind of an abstract way or like theoretical way, you should be agnostic to the relayer. It's like TLS kind of thing, right? Like the middle shouldn't matter.
Yeah.
That's what the cryptography is providing. That's what the proof's providing. In this case, though, the relayers were actually players in the ecosystem, and you needed to, I think, like stake or pay or something a certain amount of token.
Yes, you did.
To act as a relayer.
In my research, that came out to, at the time of the attack, the day of the attack, it was $28,712. So long story short, a user can be a relayer, is what Michael's saying there, because you can have anyone.
Thanks for the summary.
Yeah. And so what happens here is, as an attacker, you stump up 28 grand or 29 grand, near their amounts, and you can walk away with 600 million. So there's
what
your
percent?
Incentive.
Did you calculate the percent on that?
I didn't calculate the percentage. I really should have, actually. Sorry, I didn't. But enough is said about the ROI there. So the relayer then submits the proof that it's validated. Tokens get burned on one side and then minted on another, I think, and then transferred to the original address. So what went wrong then here? Because that sounds like a pretty stable system. It makes sense from the outset. If the crypto is always going to work, then we're always going to be able to validate the transactions. So how did this attacker walk away with 600 million?
Okay. We can try to explain that. You help keep me on line here. So So it comes down to that proof and how that proof gets validated. So there are a couple of concepts that are going to kind of mix together here, to show like where the vulnerability is. maybe starting at a high level, the vulnerability was that the proof validation didn't happen properly.
Yeah.
And it was possible for the relayer
Mm-hmm.
to insert a transaction
Mm-hmm.
And have the proof still validate. So it was possible for the relayer to make up a transaction, say this transaction happened, and have the cryptographic proof check out. When it shouldn't have, because that transaction didn't actually happen on the other chain.
That's actually a great level to explain. I don't think you need to go any deeper than that.
We just stop
then
there.
Then the question becomes, why was that possible? Now, this is where it's like, okay.
So should we actually go into this stuff about the trees and all that, though? That's the nerd. That's the nerd stuff, right?
That's the nerd
and
stuff.
Here to do some of that.
We got it because we put a lot of work into understanding ourselves. So yeah, let's go.
Okay, we still have like 15 minutes. We're fine.
Yeah.
Okay. Basically, again, kind of, we'll try to stay a little bit high level, but the actual cryptographic proof is based off of this data structure called an IAVL tree, which I had never heard of until I read about this.
I've never heard of it in my life.
But it's similar to this thing called a Merkel tree, which I did hear about in like fourth year university.
I heard about it in passing 6 years ago.
Yeah, exactly. So a Merkel tree is a data structure that you can look up. It's basically a tree. So like if you think about like your data structures class, it's a tree. There's a single node at the root. That node has two children, like a left child and a right child is usually the way it's described. And then those nodes can be intermediate nodes, and they can have children, left and right children, or they can be leaf nodes and not have children. So it's a binary tree, basically. It's a kind of binary tree. The neat application of it here is that each node in it hashes its children to come up with one hash at the end. And so you can construct like cryptographic proofs to prove whether something is, I don't know if I'm going to say this exactly right, is a member of the tree. Like to prove if some data is within the tree, because the leaf nodes are data.
Yes.
And in this case, the leaf nodes are going to be transaction data. That's what you care about.
Yeah.
So if I have a transaction and I have a Merkel tree or I have an IVL tree that has a lot of transactions, I can prove kind of quickly whether my transaction is within that tree or not, because of some nice properties that this data structure has. Is that accurate?
That's basically it. That's how I summarized it in my head. It's a very, and also it's neat, and it's not what's the opposite? What am I looking for? Basically, it's a very convenient data structure to have because it doesn't take up space, considering how many transactions could be in a given.
Yeah, because everything boils down at the end kind of to a hash.
To one hash, a fixed length hash, which is extremely clever.
Anyway, you should definitely do not rely on our explanations of this. And if you're interested in the data structure side, you can look it up. Yeah. If any of my CS profs are listening, you can direct complaints about my description of that somewhere else. But anyway, we're trying to hit on the important bits. So basically, so validating this cryptographic proof means that you have the data about kind of the transaction-ish,
the historic transactions,
and you have this like structure, and you do some hashing to validate that this is like within the structure, and you kind of find a path through the data structure to your thing. Okay. What is the next thing to say to that?
So what went wrong with that validation, right? Because they were using, the bridge uses the IAVL tree as part of its way, or in fact, as a fundamental feature in terms of validating that this transaction has happened on the originating chain. So, as you said as well later on, what the attackers realized was it was possible to manipulate this validation mechanism into thinking that a transaction that hadn't happened on the originating chain had happened and all was tickety-boo, as we say where I'm from. So, how were they able to do that? The way this tree structure was validated, there was a fundamental flaw in the way the bridge contract validated the proof. Is that a fair characterization?
Absolutely. I think that's a fair characterization.
And the reason it could be exploited is because, as you said, each of these nodes on these in this tree are literally hashed. They're basically hashed values of transactions that have happened in the past. So if you can slide in a fake transaction and have the validator proof pass, then the bridge contract goes, okay, time to do the second half of this transaction, which, as you remember from earlier in this podcast, is give the attacker give the user the equivalent of whatever they think is in that transaction, that fake spoofed, for our security engineering friends out there, what was in that spoof transaction to carry out and give them their assets and direct that to them. Is that a fair characterization?
Yeah. So basically, like we said, it was that tree structure where there's like nodes and left and right children.
Yes.
When part of validating that is you kind of walk through that tree structure and you say, here's the left child, here's the right child, hash that, hash this or whatever.
Put them together and hash for them.
The like actual smart contract code, which we could probably link the show notes because this was like open source stuff, more or less. Like you can actually look at the code, you can look at the PR that fixed this.
Yeah.
The data, each node would have data in a left or a right attribute based on, I'm going to probably get this wrong too, based on whether it was the left or right child of its parent.
That's 100%,
right?
Yeah.
And so if it was literally like the code was literally like if the left variable is null, then validate the right side because we're on the right.
Yeah. And also, why did it matter whether they're left and right? Is because how the hash was formed of the parent node. Correct.
Yes.
So basically, if you have left and right and it's both populated with data, and you're going to hash them both, basically there was a rule set that said which one would you hash first, left or right. Normally it's the one with the most amount of data. So if right had more data as a large data structure, you hash that one first, then you put it together with the hash of the left, and vice versa. So what you had to do in order to do that calculation was you had to check whether there was actually any data in left or right, then decide which one's going to go first to make the parent hash, to make up the parent hash when you put them together. So what happened with this one, and this is where you can keep me honest, is basically the contract checked, is there data in left? If there is, then you're going to hash with the left child first. Or is there no data in left? Okay, then obviously there's data right, hash with the right child first. And if there's, well, that's it. And this is where it gets interesting from a security perspective. And even, this even gave me flashbacks to my functional testing days. It was before I became a security professional way back in the day. Because as a security professional, as any testing professional, to be honest, your first question is, what if I do this? And in this one, as I just said, the check was, is there data in the left child? If there is, then hash left first. Is there data in the right? No, is there no data in the left child? Then there must be, then the assumption is there's data in the right child, hash right first. What happens if there's data in both of the children? I think I've got that wrong. No.
The left and right,
it checked. Okay.
If it was basically like if left empty, hash right.
Hash right. If
left not empty, hash left.
Hash left. But if there's data in both, then it's still hash left first.
Yeah.
That's what it did. Instead of throwing, in my opinion, it should have thrown an error of some sort, or it should have done something else. But it basically what it did was it just said, when it was always positive, whenever there's data left went first, even though you could, as a user, put data into the right child.
Yeah. So basically, like the assumption that the code, like we talked a few episodes ago, I don't quite remember when, about like security being about like assumptions and kind of encoding assumptions, and then what happens when those assumptions don't hold, right?
Yeah.
So like the encoded assumption within the smart contract code was one of these attributes is empty.
Yeah.
It was either the left is empty or the right is empty.
Yes.
And it only knew how to handle those cases.
Those cases.
The thing that can break the assumption here is, well, what if both have data? If both sides of this, both variables here, have data in them, that was unhandled. Unhandled is, I mean, kind of depends on the coding word here. That would be handled as if the right attribute was empty.
Yes, that was it. That's correct. So both, and it was still hash left first. So the thing that, as I said, it triggered me from my functional testing days because it reminded me of like decision tree testing type thing where you're like, okay, a simple example is username password. So you have a username password page. The user's going to go through this flow, put in every combination of what could happen. So they could put in neither. They could put in one of each. They could put in the incorrect one, the correct one of those. And then those become your test cases. And then you would go through, as a functional tester, I used to do this. It was not my bag, but I did it. And you'd go through and work through every scenario and figure out how the application handles. It appears as though that wasn't done here. So, and an attacker spotted that. Why does this matter? This matters, let's roll it all the way back up, is because of the way things go. Remember, the cryptographic proof says this transaction was a valid transaction on the other chain. How does it do that? It looks at the hash. If you can insert a fake transaction but not alter the valid hash, then the bridge contract says this is all valid. Even though that transaction never occurred on the original chain, you've just got a valid hash from a previous transaction. To repeat that again, what happened? The reason this matters, whether it's the left or right child, and what happens if it sees a left node and only hashes against the left node, even though there is data in the right node, is that you can basically smuggle in a transaction that doesn't alter the hash that the bridging contract uses to say that this transaction happened on the original chain, give them their assets. If you can get a valid hash from a previous transaction, smuggling your malicious code, so to speak, or your fake transaction saying that, yes, I did this thing, give me some more tokens, even though it never happened, but you've got a valid proof, then the bridging contract took that hash as gospel and gave you your assets. Is that a fair characterization?
Yes, I think so. Yeah, basically, like what this bug in the validation meant was that if you malformed the data structure, you could like hang a node onto the tree. Might be a way to put it.
Yeah,
and that node wouldn't get rolled up into the hash that ends up at the end and says this is the proof.
Exactly.
And so that bug, it could be fine. That bug could be there and not affect things if you can trust the data structure that's supplied, right? So like the other half of things here, like the other thing that needs to lock into place, like usually with a security issue, right? Multiple things need to lock into place for the problem to happen.
100%.
So the first thing is like this bug is there. Okay, like there's bugs everywhere all the time, right? The other thing that needed to lock into place was, and where there's maybe kind of another assumption-ish, is the proof that's being supplied to the bridge contract is actually in a way an untrusted input, right? If that proof was a trusted input, like let's say like the bridge itself was running the relayer and it knew that it was going to provide well-formed trees, like data structures to the bridge, it would work. It would like be working fine, right?
Yes.
But so the other thing that needed to lock into place here was that other untrusted actors in the ecosystem supplied the transactions to the bridge the bridge contract, right?
100%.
And that actually like data coming into the bridge contract could be malformed, and maliciously. So, so yeah, that's kind of the second half of things, and the part where like, well, that's why the attacker needed to become a relayer so that they could become a relayer, craft a payload, like this tree was basically a payload, right? And then submit that payload to the bridge contract.
And that's how you turn $28,712 into 600 million people. Simple as that. So this was yes, as we said earlier, researching this was a bit of a brain buster, but we got there because it was brand new concepts that we hadn't. It was old concepts we hadn't had to come into contact with for a while, or it's brand new concepts against things, bridges, relayers. I've kind of already kind of foreshadowed my thinking around this. To me, there are two major things here.
Mm-hmm.
Um, there's the not oversight, but there's the bug in the validation of the proof. That's the obvious thing, which is, and again, as I said, it just triggered my functional testing days, which is going through and testing every scenario, what happens, and making sure that you handle for that. If you're going to hang your hat, and by that I mean your entire security posture on the cryptography and implementation of that, it needs to be thoroughly tested, and assumptions need to be questioned at every, what did you call them, security boundary? I think you called them security boundaries in our previous podcast. I really like those. I think that just needs to be a given. But you know what else made me come, I was like, hold on, Binance is a centralized exchange, so that being centralized versus decentralized gives you more power in terms of manipulating what happens and what transactions can go through. How is it that, to me, this is a finance versus the real world, or Web3 thing versus the real world question to me, that I can become a relayer. You've got anonymous relayers, or basically anyone's allowed, open relayers. Anyone can become a relayer as long as they stump up the cash. But then they're allowed to submit transactions that would actually withdraw 600 million from your ecosystem instantaneously. To me, for anti-money laundering laws in the UK, you can't go into a shop and spend more than 10k without people doing a KYC check. It's obviously cars is a whole different thing and whatever. But if you walked into, they would 10 grand, they would be like, well, we don't know. You can't open an account and just transfer millions in and out of a bank immediately in Europe. But here you can set up yourself as a relayer and get access. I'm like, could they not have given them graduated access? To my mind, you've got the crypto fine, but at a higher level, at a risk management level, should you really have people who can spin up a relay and then submit a transaction? Because they would have had to have submitted a transaction for it was 600 million USD, but it was like 100 BNB, which is still a large amount. Anyone can do the math at the time, given what the exchange rate was. I think it's weird that they didn't have a control around that. Yes, anyone can become a relayer, but you should limit what relayers can do and build up trust with them. So those were the two things that came to me, which was the whole testing, the code testing and the application testing, and the what if of the scenario of going through all the different permutations of the left and right child and what to do when one is populated, one not. And then the other is outside of the code, just processes, just risk process management. Like, can you just be there and just then submit a transaction to take out X amount of money when you don't know who this actor is or what they're doing, and it's suspicious that it should be happening as they become a relayer for the first time immediately? What do you think?
Yeah, I honestly hadn't thought about that angle yet. I was like fully in like the Web3, like, okay, like transaction is transaction, is happening. like I think that comes down to kind of philosophically what you see these blockchains as, and like the whole like DeFi thing and all that, right? Like it does, like these things like have a flavor, like as we've gone through these different attacks, they have a flavor of things happening hard and fast, right? Like,
yes,
and that's that's like the crypto way, and not just crypto in like the blockchain way, that like crypto generally, like cryptography, like things happen hard and fast, right? Like something is proven or it's not, and if it's proven, then it's trusted, and if it's trusted, then you can do that, like it's very tightly integrated that way.
Yes, it almost gives me reminiscent of code is law.
Oh, absolutely. Yeah. And in this case, like then when there's a bug, then like the bug is law, right?
Yeah.
Like that's how it goes. And like, should it be that way? I think it's a fair question to ask. I think, your idea around like, how is trust represented in these ecosystems? How is the trust placed in different actors to operate in the ecosystem built up or represented or whatever? I'm sure there's like a lot of different proposals around how that can and should work.
Yeah.
In this case, though, it's basically like, again, that trust comes kind of hard and fast when it's encoded, right?
Yeah. So those are kind of my final thoughts. Sounds like those are kind of your final thoughts as well. We should just say, to put a bow on this, I don't think Binance actually recovered the money. We do think last I saw with some casual Googling, they split the money up into different wallets and then obviously put it through, I'm guessing, some laundering mechanisms. There are a bunch of chains you can do a bunch of things. Oh, I can't remember what those things are. Whether you actually spin
You mean
them.
that's what the threat did?
I
Or
think that's what.
Okay.
Yeah, that's what the
Yeah, I
actor
don't know.
did.
I honestly I didn't look at it past the
Past
like out
past
the
the good
door.
stuff.
Past the good, yeah. Rapidly lost my interest after I.
It's like I don't care about this. But yeah, so I don't think they got their money back. And as I said, it wasn't Binance's only hack. It was definitely one of the largest crypto attacks on record, even to date. Successful attack. So feel free to go and Google it yourself. Yes, and Michael's reminded me again to put stuff in the show notes, so I will, for those that want to go and do their own further research into it. But it's definitely an interesting one because, again, these abstract concepts of bridges, relayers, etc., is a Web3 native thing that I don't think we draw a parallel for in Web2.
It's tough to think of a parallel for those concepts.
Yeah, no, I mean, yeah, exactly. I think actually in the financial system, in the physical world, where you have corresponding banks between different nation state banking systems, maybe. But anyway, let's not go down that road because then I'm definitely out of my wheelhouse. But otherwise, yeah, this was an interesting one. I want to say thank you, Michael, for bringing this one to our attention. This was a cool one. Yeah, thank you for listening, and we'll be back in 2 weeks' time.
Thank you.
Thank you.